for ELEX 420 students. Had some issues with predicting the voltage ripple and the DC and RMS values for half wave or full wave rectifiers with an RC output. So I'm doing this video for clarifying this issue. Sorry. So first, let me remind you that we had two periods in the RC circuit response. If you look at the voltage, first we have a charging period, and then we have a discharging period. Charging and discharging, and then again charging, discharging. And we want to find the intersection between this waveform or this graph, this plot, and this one. This one, it's an exponential function, and this one, it's a sinusoidal. Whenever we want to find the cross section or intersection of two waveforms or two plots, we just have to make their equations equal. Something that we have to notice that for this exponential and this sign, the intersection would give us the initial conduction angle, which happens every period. So here, like, we would have another one here, and then again like another one period after this. This is for a half wave rectifier. Now, one thing about this two waveforms is that we have the equation of this one, we have the equation of this one as well, but their origin or their reference, it's different. Okay, so the equation for this one, if you remember, it was V peak times e to power negative t over tau, and tau was the time constant, and for this one it's just V peak times sine of omega t. But for that equation, the V peak times sine omega t, the time origin is here. But for V peak times e to power negative t over tau, the time origin, it's here. And that's why you see a time shift here, because the difference between these two, it's the it's the final conduction angle, which is if you remember, for half wave rectifier was t over 4, as you see here. This is like for half wave rectifier. Okay, and single phase half wave rectifier. And you see that this equation that we have to solve, V peak times sine of 2 pi f, this is omega, times TCI, which is the time at this point, it's equal to V peak times e to power negative TCI minus TCF. So we end up with this equation. Now here we know f. This is for the input. It's, for example, 60 or 50 hertz. So we have everything except the initial conduction time or initial conduction angle. And on the right hand side, again, we have R, we have C, and the TCF, T sub CF, it's T over 4. So this is an equation, one equation, and the only unknown is the initial conduction time. Now, this is unfortunately a non-linear equation. Okay, so it is not very easy to solve unless we use numerical software packages or engineering calculators, scientific calculators. And here you see that in your course notes on page 9, You see that Dr. Jeff plotted this in MATLAB, and we can see that, oh, we have the initial conduction time, and we know what the voltage is at that point actually. So that's very interesting. Now, how before I show you how to write that program using MATLAB, I also wanted to show you that we can also use MATLAB Simulink, which is a graphical circuit simulator, graphical software package, similar to what you do with PSpice and Multisim, but we can also use many examples that exist in Simulink. So what I only did was in MATLAB platform, I wrote this command, which is the command for this example, which is one of the default examples from MathWorks. So SSC bridge rectifier, it's a full bridge diode rectifier, and this is an RC circuit. So you see that this is like for full bridge, we can see the waveform and we can create everything, so it's good for practicing. Now, for the half-wave rectifier, as I mentioned, we have a conduction or charging period and discharging, and this is like only happens in the first cycle. After that, we end up with the what we call AC steady state. It means that we have a waveform that repeats itself every period, and this period, it's the same as the input period for the half-wave rectifier. Okay, so this is the charging part, this is the discharging part, or conduction and discharging. And here you also can see the current that goes through the diode. Okay, and here we also know that if we have the delta V, we can find the time, and then we can find the angle as well, right? We can find time, and omega t is equal to theta, so we can find the angle. The final conduction angle, which is this point, it's always t over 4. So the final conduction the final conduction time, it's t over 4, and the final conduction angle would be always pi over 2 radians or 90 degrees, and we can find the conduction angle or conduction time. And so we know that conduction time plus the discharge time would be equal to period. From here to here, it's 1t, 1 period. So once we have the conduction time, we can find the discharging period, which is shown here. Okay, so these are like from your course notes. So all of them are from your course notes, lecture notes. Now here I wanted to show you something from MATLAB's help or document. There is a symbolic toolbox in MATLAB that it's very helpful for doing some calculations, integrations, differentiations. So it's a very good toolbox. I am not sure if you have installed it in your MATLAB. If you haven't installed it, just like make sure that run the installation file and the exe installation file, and then just like select the symbolic toolbox. Once we have this, we can actually solve equations like this non-linear equation that we have here. We can solve it using MATLAB. So here you see that how you can solve. There are two solutions, two solve files. One is just like solve, the other one is VPA solve. This one, it's using the symbolic toolbox. solution, sometimes it's not very helpful and you get a warning. In this one, it's a numeric solution. So I did this example for you guys here. So I'll go through this code here and how this plot was created, and you can just like follow the same code that I wrote here, and you create the same graph. So here I'm just like clearing the variables, like the workspace, closing all the figures from before, clearing the screen, clearing the command window. These are the parameters. So I assume that the F, the frequency of the input AC waveform, is 60 Hertz. The capacitor value is 1 millifarad. R is 10 ohm, resistance is 10 ohm. There is no forward bias voltage, 0, so ideal diode. And V peak it's 120 times root 2. So basically the input AC voltage is 120 RMS volts, and this is the peak value. I calculated tau, the time constant for the RC circuit. I calculated the period, and as I mentioned, the TCF, it's T over 4, one quarter of the period. Then here I'm mentioning that on line 4, I'm mentioning that I'm basically specifying that TCI, it's my symbol. This is like a variable, like similar to variable. I could call it X or T or whatever I wanted. And here, this is the equation that I wanted to solve, right? This is the same equation that that it was written in the lecture notes. Once I solved it using, in line 6, you see that I used the symbolic solution and I got a warning, okay? And because of that, I wanted to get a better solution. I also find you see that here, TCI underscore rad or radian, it's another variable I defined to find the numeric value between T and 2T. I also wanted to plot the left hand side and the right hand side. That's why like I didn't use the simplified version of the equations. So this is the input, and this is the exponential function, okay? But remember that here, like I'm plotting both of them from the same time origin. And this, but like just like it hits this one at this point, right? Actually it's not, sorry, it's not the same time origin. Like here, like this is the V peak, but like I'm plotting it with the same time origin, but the equations are like from here to here. That's why like there's this time shift here. Now also, like after you run this code, you can find what we want to find here. It's TCI. So we find the initial conduction angle, but you remember that this one, it's for the next pulse. It's for the next pulse. So this is the actually the second initial conduction time, okay? So it's the second initial conduction time. The first one, it's just one period before this. Now here you see that the initial conduction time, it's given here. You can see that like I am zooming, I basically using a probe to find the values, and X is the T, and I also have the Y, the basically the voltage. Even if I didn't have even if you don't use the graphical plot, you can just like plug in TCI into the equation and find the delta V. So here you see that here, based on this solution that we find, the delta V, the ripple, it's from here to here, right? From here to here, and we know that this point is V peak. We assume that there is no forward bias voltage drop on diodes. Okay, so the delta V, it's in this case it would be from this point minus here, but I also wrote the code to calculate delta V. Okay, and the first initial conduction angle, I also found it here. So I just like subtracted one period to go one period back, and this is the first conduction angle. So this is how you can find delta V, the initial conduction time, and the initial conduction angle. Just like a review of the concept of DC RMS and AC RMS values. So these are the formulas for DC and RMS value of X, for example, function X, the periodic waveform X. So the DC is just like the average, right? So 1 over T integral over one period. Doesn't matter if it's from 0 to T or from any number, like let's say T over T plus T, capital T, or A until A plus capital T. The difference between the upper and lower limits should be capital T, the period. That's it. It's just the average over one period. For the RMS, it's root. We have a root, and then mean, like mean, right? Just like the mean involves like averaging 1 over T squared. So averaging 1 over T integral over, again, one period squared. Okay, and because these signals, these time domain signals, are periodic, that's why I mentioned it doesn't matter if it's from 0 to T or from any number A to A plus capital T. And also here, these are from your lecture notes. It's shown here that do to find DC RMS and AC RMS for this waveform that we have, it's to do that integration from here, let's say like from here, from TCI up to one period after. Okay, if we want to do integration, you just remember that from here to here we have one function which is sinusoidal, and from here to here we have another one which is exponential. That's why, like, when I did the integration, I broke it into two integrals, right? So that's again, I use the symbolic toolbox of MATLAB, and this time I use the int function, short for integral. Again, this is from the document of and help of MATLAB. So you see how you can get indefinite and definite integral of functions using symbolic toolbox of MATLAB, and using the formulas that we had for DC and RMS. I calculated the integrals. Again, you see that like I have one integral here for the sinusoidal and another one for the exponential. I had to change the limits because these two have a time shift that it wasn't considered here, so that's why like the limits, I changed the limits here. I hope I didn't make any mistakes, but I think the results made sense. But like I might have sometimes we can assume it's very small compared to the whole period. So this one also might look like a line. But sometimes like people like only consider this one sinusoidal, this one a line, but like sometimes we can assume both of them are linear, right? And but this is like an approximation, this is a simplification. Why can we do that? Because like we have series, I'm not sure if you've seen them in your math courses, they're called Taylor series. That would basically give an approximation at a certain working point for nonlinear functions like sine and exponential. And you see that sine of x, it has this format. This is an indefinite, like infinite series. So there should be plus dot 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 ellipsis, I think that's what's called. But anyways, so you can see that like if we ignore or remove the higher order terms, you see that we can approximate sine of x with just x. That would be a linear approximation, right? So you like for here, like the working point, it's around 0, right? It is exactly 0, sorry, it is exactly 0. And this is an approximation that we like always have. We say that sine of x close to 0, it's very close to x. Now like if you want, you can change the working point. The same thing for exponential. So it can be written as infinite, as a summation of an infinite series. If we only consider the first two terms, it's going to be a linear approximation. So that's why like we can sometimes make these approximation. And for a if you make that approximation, the charge and discharge would become a triangular behavior. And for a triangular waveform, we can, or a sawtooth waveform, just like a periodic triangular waveform, we can find the DC and RMS values this easily. Okay, so these formulas used in some textbooks for an RC circuit. This is an approximation. It doesn't matter if you want to use the approximations or the actual formula from MATLAB simulation, but this one sometimes it's easier. For other rectifiers, full wave, single phase rectifiers, or in your lab 2 you have to work with 3-phase rectifiers. It's the same story, but this time TCI, or sorry, TC, the conduction time plus the discharge time. This time for the single phase full wave rectifier, it is half of the period of the input. It's half of T. Okay, and if you remember for 3-phase, this one becomes 1/6 of the T, right? Because it's a 6-pulse 3-phase rectifier, so we have 6 conduction periods per cycle. Okay, so it's the same story. The only difference that you would have, it's that your TCI and TCF, they are gonna be closer to each other. Okay, so that's gonna be the only difference. I hope that helps you with your